Uh, there are many compounds in the cell that function as buffers, and these are usually weak acids or weak bases, and they're usually represented in this way. When the weak acid here, when it reacts with water, will give us a hydrogen ion or hydronium ion plus the what's equivalent to the hydroxide ion, but we refer to it as a conjugate base. All right, and the conjugate base, when it's in equilibrium with the weak acid, can function as a buffer. This has a equilibrium constant association for the acid, which is equivalent to the concentration of products over the reactants. Okay, and we then can apply our convention for our hydrogen ion concentration to the acid dissociation constant, and this will give us our Henderson-Hasselbalch equation. We use pK plus the log of the conjugate base over the weak acid. Okay, and pK is equivalent to the negative log of that acid dissociation constant. So by taking the negative log of both sides, we reduce the equation to get this. And we can determine the pH of a solution if we know the concentrations of the conjugate base and weak acid and the pK value, which we can look up in a table, particularly for different biological weak acid compounds. All right, and finally, in our chapter 4, we dealt with a number of acids which are involved in creating our proteins. Okay, these are what are called amino acids. Okay, this is the acidic portion, this is the proton donor, and the amino portion is on this end. And at neutral pH, this is usually negatively charged, this is usually positively charged, pH equal to 7.4. And if, let's say, this was a, which amino acid is this? This is threonine, THR or T. And so we look at this structure, we see that it's charged at pH 7 because the pK, that is the point at which the carboxyl group will begin with the carboxyl. The point at which the carboxyl group loses or gains a proton. Okay, so we can represent this carboxyl in this way. This is the weak at equilibrium. The pK for this alpha, remember this is the alpha carbon, alpha carboxyl group, is equal to 2.2. The nitrogen also can dissociate. Alright, and this is its conjugate, which is neutral. And the weak acid, which can donate the proton, is positively charged. Conjugate base. Its pK, alpha amine group, equals 9.4. Alright? 9.4. So we can look at this and what you usually get, I'll try to render it here in this section here, is a curve as pH goes up. Hydrogen ion concentration is increasing in this. Have a plateau here. And this center of this plateau is usually where the pK is for that functional group, COOH to COO minus. Again in equilibrium at this point. And as we go tenfold increase in the concentration of our conjugate base, we go up to a pH of about 3.2. This is the end of the titration. This is the end of the plateau. And the beginning is about 1.2 or 1 pH unit below. So plus or minus 1 pH unit equals plus or minus 1 pH unit is our buffer region. And of course, as we continue to add base, we reach another plateau, which is where the amine group loses its proton to form its conjugate. And again, it's plus or minus 1 pH unit above and below pK, which is equal to 9.4 for the amine group, is also our buffer region up at this end. Okay, so hopefully this is this was a little summary of what we covered in chapter 2, and also a little bit about what we covered in chapter 4 concerning amino acid structures. Again, you need to know those structures, understand where the alpha carbon, the carboxyl, and the amine groups are and what they mean in terms of the structure of the amino acids, what the side chains mean, which ones are polar, charged or uncharged, and which are non-polar. Okay? All right, I'll see you in class.